In recent times, authoritative statements have emerged suggesting that the law of energy conservation is being violated in cosmology. However, an analysis of the motion of cosmic photons in bidirectional, that is, symmetric, time confirms that the energy conservation law is, in fact, being maintained in cosmology. We will make a distinction between cosmic time and parametric time. Parametric time progresses evenly and is associated with a specific photon. An important parameter is the time of the photon's existence delta t, during which its wavelength increases. Cosmic time is related to the expansion of space in a stationary universe and originates from the Big Bang, ending in an everlasting present, t sub 0. We assume that a cosmic photon is emitted at time t sub 1, according to cosmic time, which corresponds to zero value of parametric time, t equals 0. This photon is then registered in the present t sub 0 after a parametric interval delta t. Similar to the standard cosmological model, we assume that the redshift of a cosmic photon is due to the expansion of space over time. It is meaningful to distinguish between the growth of the photon's wavelength and the increase in relative distances between galaxies, more accurately, galaxy clusters. For the first case, I propose introducing a coefficient of increase in the photon's wavelength, denoted as alpha, or wavelength factor. This can be defined as the ratio of the final to initial wavelengths of the cosmic photon. This coefficient is dependent on parametric time, more precisely the number of oscillations completed by the photon during its existence delta t. The wavelength factor is an attribute of the photon, not the space. Nevertheless, it is by this factor that the scale factor, A, is determined, which, as mentioned before, characterizes space. This factor depends on cosmic time t large. In a certain sense, this value is conditional. At the moment of the present time, whenever it occurs, in the real current present or in the past, it is taken to be equal to 1. Therefore, at the moment of registration, the scale factor is equal to 1. At the moment of emission, it represents the inverse of the wavelength factor of the registered photon, that is the final photon. There are two key events in the life of a photon: emission and registration. Only at these moments can an observer perform real-time physical measurements, measurement of the wavelength of the actual cosmic photon, or its identical laboratory analog, by directly measuring and then comparing the wavelength of the registered photon with its laboratory value. An Earth-based observer determines its wavelength factor, alpha, which turns out to be some value, A, greater than 1. From this, it is concluded that the scale factor of space, at the time of emission t sub 1, was A times smaller than the present one, taken as unity. The wavelength factor of the photon alpha, at the time of emission t sub 1 is equal to 1. For physical reasons, it cannot be otherwise. At this moment, when the parametric time of the cosmic photon was 0, its wavelength was equal to the laboratory value of an identical photon. An observer near the source, a star-based observer, for whom t sub 1 is the present moment, could have confirmed this. However, if an Earth-based observer measures the wavelength of the photon just emitted at that past moment, metaphorically speaking, across the thickness of time, he will find that it is A times shorter than the laboratory value. In other words, the initial wavelength factor of the photon alpha, from the perspective of the Earth-based observer with his standard ruler, is A times less than 1. This implies that the wavelength factor of the cosmic photon, alpha, has grown by a factor of A squared, whereas the scale factor of space has only grown by a factor of A. Put differently, the growth in the wavelength of the photon is faster than the increase in the relative distances between galaxies, which contradicts the postulate of the standard cosmological model. The redshift should align with the expansion of space, since it is caused by it. A pernicious practice has emerged of discarding the solution to the homogeneous wave equation that corresponds to motion in the opposite direction of time. This action is justified by the fact that processes moving backwards in time are not observed, and furthermore, it violates the principle of causality. From the perspective of consistent Pythagoreanism, a theory that arbitrarily discards solutions cannot be correct, or at best, complete. To account for the complete change in the wavelength of a cosmic photon, quadratic redshift, red square, was introduced. The quadratic scale factor and red square naturally arise from the symmetrization of time in cosmology. These innovations help resolve the dark energy problem, as well as Hubble tension, and the age problem of the universe. References to the relevant works are provided on the slide. A recent study performed at the University of Toronto points to the occurrence of negative time in quantum processes. During the experiment, it was found that photons can exit a material before they enter it. In my opinion, symmetric, essentially reversible, time should behave that way. Time symmetrization in cosmology has a peculiarity. It is essential to account for the fact that the space of the universe expands in the direction of the future and contracts in the opposite direction. Therefore, reversing time is not confined to merely changing the sign of the time parameter. The question arises, how can one illustrate the movement of a photon in symmetric time, while retaining both alternative solutions of the wave equation, with both positive and negative time parameters? This slide presents an option for a scheme of such motion. A source at some present moment emits two photons, each in its own direction of time. One photon undergoes wave motion from the present into the future, while the other moves in the opposite direction, from the present into the past. This other photon can be called an antiphoton, in line with the hypothesis of John Wheeler that a positron is an electron moving in reverse time. Thus, the wavelength of the photon increases over time, in accordance with the scale factor of the future space in which it travels. Meanwhile, concurrently, the wavelength of the antiphoton shortens as it travels through space of the past, the scale factor of which decreases the closer it gets to the singularity. The event of emission, like any completed event, remains forever in the past. Moreover, over time, the moment associated with this event becomes increasingly remote from the current present moment, into the depths of the past. This is also true for the moment of emission of the photon-antiphoton pair T1. Both components of the emitted pair maintain the same initial frequency, and are characterized by a unit wavelength factor. A photon which is departing from a double source in the right direction, into the future, is, in reality, always in the current present moment, where a potential receiver, in our context, the Earth observer's detector, is expecting it. The wavelength of the photon increases as the interval between it and the source grows, that is, with the passage of parametric time. At the moment of registration, the wavelength factor of the photon, alpha, reaches some value, a. On the contrary, the wavelength of the antiphoton decreases over time as it moves away from the double source towards the singularity. At the moment of registration, its wavelength becomes a times less than laboratory value. At the final moment of the pair's existence, the wavelength of the photon is a squared times greater than the wavelength of the antiphoton. To a terrestrial observer, the antiphoton, traveling along the cosmic time axis at double speed, finds itself in a more distant past than the emission moment of pair T1. Over the pair's lifetime delta t, the antiphoton reaches a certain moment T2, for which the scale factor is equal to 1 to a squared, which is a times smaller than at T1. Therefore, during the pair's lifetime delta t, space expands to the same extent as the photon wavelength increases compared to the antiphoton. In other words, in cosmology with symmetric time, the redshift is consistent with the rate of space expansion. If Wheeler's assumption that an antiparticle is a particle moving backwards in time is correct, then it can be stated that an antiparticle moving forwards in time is indeed a particle. In our case, An antiphoton traversing from point t sub 1 to point t sub 2 along the cosmic time axis is indistinguishable from a photon traveling from point t sub 2 to t sub 1. Reversing time results in cause and effect being switched. In our case, the final moment of the antiphoton, t sub 2, becomes the initial moment of the photon, with its final moment now being t sub 1. The emission of a photon-antiphoton pair at that moment t sub 1 can be considered as the ray emission of the photon. Over a total time of 2 delta t, the final wavelength of such a composite cosmic photon, formed by the inversion of the reverse component of bidirectional time, increased, while the initial wavelength decreased by a factor of AE. The cumulative increase in the wavelength factor of the complex photon, alpha, corresponds to the enlargement of the scale factor of space, AE, over the total interval between t sub 2 and t sub 0. Thus, an antiphoton in reverse time is indistinguishable from a photon in forward time, as depicted in the given image. An antiphoton released at moment t sub 1 seems to be a photon that was emitted previously, at moment t sub 2. In other words, such a reversed photon, let's call it dark, following the established tradition in cosmology, has changed its temporal orientation and is traveling along the time axis from its newly acquired source at point t sub 2 towards point t sub 1, where it was truly born. Now, at this point, instead of the emission of a photon-antiphoton pair, another event occurs, the ray emission of the photon. The motion of the other, light photon, which has preserved its orientation, comes to an end at the present moment in time, t sub 0. In cosmology with symmetric time, the law of conservation holds true for the total energy of the photon-antiphoton pair. Suppose, at the emission moment t sub 1, the source released a cosmic photon with a frequency of nu sub 0, as seen by a star-based observer who can measure the initial wavelength of the freshly emitted photon. The total energy of the photon-antiphoton pair is 2h nu sub 0. Question: what will be the total energy of this pair at the registration moment t sub 0? It is assumed that an Earth-based observer measured the redshift z, and thereby determined the scale factor, A equals 1 plus z. The result of this measurement indicates that the frequency of the photon has decreased by a factor of A, while the frequency of the antiphoton has increased by the same proportion. Therefore, the sum of energies became equal to this value. Employing the known formula, we arrive at the desired equality. The energy of the photon pair at registration is the same as its energy at emission. Accounting for the relativistic correction due to the source's velocity beta, relative to the Earth observer, this equality indicates that the law of energy conservation in cosmology holds true. It is proposed that the developing cosmological model with symmetric time be named Temporal Cosmology.